Okay. All right, let's settle down. Last lecture we were discussing deterministic finite state automata. So they are a very simple kind of machines, right? They have you can think of them as programs which have fixed memory, which doesn't increase with the size of the input. So they're a limited model of computation, but we saw that they can do some interesting things. So let's just to recap. We didn't do this example because I wanted to finish other things. So just as a way to get back into DFAs, let's try to figure this out. Design a DFA to accept all bit strings, right? Which are basically, you think of them as binary strings, right? Or they are numbers in binary, and their mod should be 5. Okay. So this is different from saying the length of the string should be divisible by 5, right? So what this is saying is, look, you know, okay, let's see. Okay, so you look at the string such as 1010. What is that? That's the number 10, right? So that's divisible by 5, and we should say yes, right? The machine should accept. But the number 1101011 in binary, what does it mean? In decimal, that is 107, right? And if you take the remainder mod, modulo 5, what do you get? You get 2, so you should not accept that. Okay. So how would we design a DFA for this, right? So what should we remember? See, so remember when, in DFA, you see a portion of the string, right? You may have seen a long string, and then you can only remember a little bit, right? A fixed amount, okay? And so that is enough to continue reading the rest of the string and still be able to decide what we want to decide, right? That's the idea of DFAs, right? So what do we want to decide here? It's whether this binary number is divisible by 5 or not, right? Okay, so we've seen, say, the first portion of the string, right? So if I see 1, so that's, I know what that number is. What should I remember, okay? Well, you know, we can say, okay, you know, at the end, I need to remember what's the remainder mod 5, right? Okay, so the natural thing would be, just like with the length, to say, you know, what I will remember is, if looking at the string I've seen so far, think of it as a binary number. What is its remainder mod 5? Okay, so is it 0, is it 1, is it 2, is it 3, or is it 4? Right, just like we did with the length. So our states could be, okay, 0, 1, 2, 3, and 4, right? So what is the meaning of this state? That of the string I've seen so far, thinking of it as a binary number, what is its remainder mod 5? That's the meaning of this, right? Now the question is, when we see the next character of the string, is this information sufficient to maintain what we want, right? Does that make sense? Yeah, okay, so what happens, I've already seen some portion of this, right? So then what do I see, right? You know, well, you know, if I see 1, and what is the remainder? If I just see 1 and the remainder is 1, right? And then I see 1, the next one, what is the number now? 3. Can I figure out what is the remainder mod 5? Okay, for 3 I can, but if I have seen a long string so far, and the only thing I know is that its remainder is mod 1 mod 5. I don't know what the number is, but the only thing I know is that it's 1 mod 5, right? And then I see a 1. Can I still figure out what the remainder is mod 5? No? I claim you can't. Why? Okay, so suppose I saw, I don't know what I saw, right? You know, let's say, okay, so let's take 1, 1, the same string, 1, 1, 0, 1, 0, 1, 1, right? I saw this long string, and I only know that, whatever I saw, the remainder was mod 2, okay? And then I see in the next bit 1, or let's say next bit is 0, okay? What is the new number? Well, I don't know the new number, but what do I know about that number? If this represented the number A, I put 0 here, what is the value of that number? 2A, right? Okay? So I don't know A, but I know A mod 5, right? But now what do I want to compute? I want to compute 2A mod 5. Okay? All right? Okay, if I know A mod 5, can I compute 2A mod 5? You don't need to know A, right? Okay? If I tell you A mod 5, and I don't know what A is, but it is, the remainder is 2, what is 2A mod 5? Okay? 2A mod 5 is, okay, it is 4, right? Do I need to know A? Okay, right? So what is that? So what is the formula for this? 2A mod 5 is A mod 5 times 2 mod 5, right? Okay? Is that okay? Okay, so I don't need to actually know A. I'm keeping track of A mod 5, right? I already know what A mod 5 is. So I multiply that by 2, then take mod 5, then I know what's the mod of the new string, right? Okay, but what if it was the next bit was 1? If the bit was not 0, but the next bit was 1, what is the number now? If A was the previous number and I get 1 after that, what is the value of that number? 2A plus 1, right? Okay. So I know only A mod 5, but I can compute 2A plus 1 mod 5 by taking A mod 5, multiplying by 2, adding 1, and then taking the mod 5. That's all fixed, right? Okay. So if I have, so from that, if this is my start state, right? Okay. What should I do if I see a 0? That means that so far what I've seen remainder mod 5 is 0. Now if I see another 0, what is the number? It is 2 times the whole number, right? If A mod 5 is 0, what is 2A mod 5? 0. So I stay where I am, right? What about if I see a 1? It is 2A plus 1 mod 5, right? So where do I go? 1, right? Okay, good. Okay, now so we know, okay, well, now what about from 1? If I am at 1, that means that so far the number I've seen remainder is 1 mod 5, right? And now I see a 0. What does it mean? So the number is some multiple of 5 plus 1, and now we multiply it by 2. So the remainder will be what? On 0 I get 2, right? Okay. Okay, but what if I see a 1? Okay. Okay, so now you see the idea, right? You can fill out everything else, right? Okay. So okay, that's so it's a little bit more involved, but you have to figure out that it's enough to remember just the mod of all the string you have seen so far. Okay, all right. Okay, that is just to recap DFAs. Let's go to these operations we defined. What we were trying to do here was something more abstract, right? So the question we want to answer was, remember regular languages we defined as all those languages which start with some base cases, and then we said, okay, they are closed under what operations? That means, if I take the union of two regular languages, we said that is also regular, right? And then we said, if you take the concatenation of one regular language and another regular language, that's also regular, right? And then we said, the cleany star is also regular, right? Okay, now that was the regular languages. Then we defined a different model of computation using DFAs. So we know that DFAs can recognize certain class of languages, right? Later on, we'll prove that in fact they are exactly the same as regular languages. It's not obvious, okay, that is true, right? Okay, so but the DFAs can do something, right? They can recognize a class of languages, right? It is again not obvious that not all languages are regular, right? But we will see that too. So we want to understand the following thing. Oh, look, I designed a DFA to recognize all strings that say end in 0, 1, okay? So we can figure out a DFA for that. Now what I want is, can we design a DFA for all strings which are not in that language? That means which are not ending in 0, 1, right? So it's a complement of the language, right? And we saw that, yeah, we can do it because it's very easy, because we take the DFA for the language we have already, right? And say, oh, let's take all the accepting states and make them non-accepting. All the non-accepting states become accepting. Then it is easy to see that, if the old DFA accepted a string, the new DFA will reject the string. If the old DFA rejected a string, will accept the string. The new DFA will accept the string, right? So the language of the new DFA, by flipping the accepting states, is exactly the complement of the language accepted by the old DFA. Okay, that was reasonable, right? So that was a powerful operation, because with regular languages, it was not obvious that we can complement and still make it regular, right? So we had difficulty saying, oh, how do we figure out a regular expression for all strings which don't have 0, 0 as a substring? It was not easy to figure out how to write a regular expression for it, right? But with DFAs, it's very easy, right? We just flip the accepting states and we can easily get the complement. Okay? Okay. So the other operations we would be interested in are intersection and union. Okay. So if I give you a DFA, if I give you a language and then there's a DFA for it, and I give you another language and there's a DFA for it, we want to know whether there is a DFA to accept their intersection, right? Is there a DFA that accepts their union? Okay. It's not obvious that you can do that with DFAs, right? For any specific language, you can say, I want all strings that end in 0, 1 and have odd length. Okay. You may then say, okay, let me figure it out. I know, we can do it from scratch, right? Let's figure out how to design a DFA for that specific language, right? But what would be nice is, oh, look, I already know how to design a DFA for odd length strings. I already know how to design a DFA for strings ending in 0, 1. If I can mechanically put together, because I want both of those properties, that would be nice, right? That means that that's a powerful way of thinking about it. And how did we think about this? We said, well, if from a programming point of view, what we want is that if you have a string, we can think of it as, oh, let's run the DFA on the string, the first DFA on that string, let's run the second DFA on that string, and if both accept, it's in the intersection, right? But the trouble is that we want a DFA, right? Not a program, which is very powerful. So what we want is a very restricted kind of machine. And as I said towards the end of the class, the idea of designing a DFA for the intersection or union is, let's simulate both M1 and M2 in parallel, right? That means, we say, okay, look, we remember this new program is going to run the old first program on W and the second program on W simultaneously. Not wait till it sees the whole string and then start M2, right? What does it mean to do it simultaneously, right? The new program is going to remember whatever the old program was remembering after seeing the prefix of the string, and whatever the second program was remembering it after it saw the prefix of the string. It is going to remember both, right? And then keep moving as both of them are, and at the end it can say, oh, did M1 accept? Did M2 accept? Yeah, okay, good, then I'll accept, right? That's the idea, right? So that's how we do the product construction, it's called. And so here is an example, right? So there is one machine on this side. it accepts all strings where the number of ones is odd. Okay? Can you see that? Why it does that? Okay? So what is the meaning of the state? The meaning of the state 0 there means that the number of ones is 0 mod 2, right? And the meaning of 1 in the state is that the number of ones is 1 mod 2, right? And we want to accept odd number of ones, so whenever a 1 comes, we go back and forth, we flip. If it's a 0, we stay where we are. Okay? And that program is counting the number of the parity of the number of zeros, right? Not number of ones. It's counting the parity of the number of zeros as opposed to ones, right? Okay. Now we want to find a DFA that accepts only strings which have odd number of ones and odd number of zeros. Okay. All right. If you want to do that from scratch, what would you do? You would say, okay, I have to keep track of both the number of zeros and the number of ones, right? Yeah. So that's exactly what we'll do in this product machine, but it's mechanical. We're not doing from scratch. Our new DFA will have the states of the new DFA are, each state corresponds to one state of the old DFA, to the first DFA, and another state of the second DFA. Okay? And then it is going to simulate both of them. What does it mean to simulate both of them? Right? So I'm keeping track of both of their states, right? This machine was in this state, this machine on this state. I see a 0 now. What should I do? Well, the first machine on 0 will go to its own state, right? And the second machine on 0 will go to its own state. That's my new state because I'm keeping track of both of them. Yeah? So that is a product machine, right? All right? Yes? Okay. And how do we do it mathematically? What is in generality, right? Because we have to do it for any two DFAs, not just these examples, right? So what is the mathematical notation for that? So I have one DFA M1 which has Q1 sigma delta 1 S1 A1. That's the first machine. The second machine has that should be Q2, not Q1, sigma delta 2 S2 A2, right? The number of states can be different, but they're on the same alphabet. They should be on the same alphabet, otherwise it doesn't make sense. Now I want to create a new DFA. And what should the states be? Yeah. We're not doing union, we're doing a product. Okay. So I will see that mathematically and I'll go back. Okay. So it's not the union actually, it's a product that means that I have to remember its state and I have to remember my state. Okay. So yeah, that's the important point. It's not the union. So let's see the thing. Okay. So what? Yeah. Yeah. Otherwise, we are thinking about union of two languages over the same alphabet. Otherwise, we take the union of the alphabets and then work with that. Yeah. You can do that also. Yeah. We assume a super alphabet of that. Okay. So what should the states of the new machine be? Yeah. The Cartesian product, what does it mean that, right? It is one, I'm remembering the state of machine 1 and the state of machine 2, okay? I have to remember both parts of it, right? I could be any of the states of the machine 1, I could be any of the states of this machine 2, right? Okay. So for every state of machine 1, I should have a separate state of machine 2 that I can keep track of. Okay? Yeah. Yes, exactly, right? So the number of states is growing, right? Okay? So the states of the new machine are all pairs Q1, Q2, right? Where Q1 belongs to big Q1, capital Q1, and Q2 belongs to capital Q2, right? Okay. So how many states are there? If N1 states in machine 1 and N2 states in machine 2, we have N1 times N2 states. Right? Okay? Okay. Now, what is the start state? Right? Well, the start state of machine 1 and start state of machine 2, that's where I start, right? So it will be S1 comma S2. Okay? Yeah? And what is my transition function? This is very important, right? So what should the machine do if it is in state Q1, Q2? I mean, remember Q1 is belongs to the state space of the first machine, Q2 belongs to the state space of the second machine. What am I doing? I'm blindly simulating both of them, right? So I look at what the machine 1 does if I see a letter and what the machine 2 does if it sees a letter, and just move along that way, right? What does it mean? That means it is, I just follow what the machine 1 does for the first state, the first part of the state, and what machine 2 does for the second part of the state. That's the meaning of simulating them in parallel, right? Yeah? Okay? Okay. And what should my acceptance states be? Remember, I'm trying to recognize the intersection. What does it mean that, I want to, when should I accept a string? If the first machine accepts and second machine accepts, right? That's the intersection. So when will the first machine accept? On what states? A1, right? When will the second machine accept? A2. Any of those is okay, right? So my acceptance states are A1 times A2, or another way of saying it is Q1, Q2, where Q1 is an accepting state of the first machine, Q2 is an accepting state of the second machine. Okay? So it's not, I mean, if you're, yeah. Sorry? Yeah, it's a tuple, two things. And it has two, remember what does delta 1 Q1A do? It gives a new state in capital Q1, right? Yeah, okay. Okay? It's a mechanical construction, right? So this is great, right? If I have a DFA for language 1 and a DFA for language 2, I have mechanically created DFA for language for intersection L1, intersection L2. Okay? Okay, before I prove anything, let me, here is the theorem which says that this machine accepts L of M1 intersection L of M2. Yeah. No, all states will be used in, I mean, even for a given DFA, what is the guarantee that all states are used? But are you guaranteed that even for a arbitrary DFA? Yeah, so it's no guarantee. Yeah, and we'll see later on that there's a minimal DFA. Okay, let's do, just to understand this. What about I want to do this, right? I want to do the same thing, but I want to accept the union of the two languages, not the intersection. What should I do? So what does it mean, the union of the two languages? I should accept the string if M1 accepts or M2 accepts. Okay? So I claim that the only difference is that we figure out what the new accepting states are. Nothing else changes, right? Because we are going to simulate M1 on W. We are going to simulate M2 on W. That's what the new machine is doing, right? And eventually we have to, the only thing that changes is at the end of the simulation we have to say, should I accept it or not? Well, what am I trying to accept? The union, not the intersection, right? What is the definition of accepting the union? If M1 accepts it or M2 accepts it, I should accept, right? It is not required that both of them accept, right? So what should the accepting states of this machine be? Nothing has changed from the previous construction. The only difference is in what are the accepting states of the new machine. Yeah, but think of it as, if both of them, remember my state is this. It's a tuple, right? The state of the first machine and the state of the second machine. In intersection, I'd say, both of them have to be good, right? In the union, what should it be? Yeah. Yeah. So that's formally that is right. Another way of thinking about it is, it's a pair of all Q1, Q2, where Q1 belongs to A1 or Q2 belongs to A2. Okay. So we can either do it that way. So Okay, so that's one way of writing, right? Right. So this is all tuple, all states, such that at least one of them is an accepting state for one machine, right? Either Q1 should be in A1 or Q2 should be in A1. And as he said, the mathematical one way of writing this is A1 times Q2 union. This is the same as Q1 times A2. Okay, right? Okay, this is just the definition. I mean, the fact that these two are equal is just a symbol manipulation. Okay, so what is A1 times Q2? This is a set of all pairs, right, where the first coordinate is in A1 and the second coordinate I don't care, right? It could be anything. It could be accepting or non-accepting, right? And so those are all fine, right? Because the first machine is accepting them, right? And the second set is all of the tuples where the second coordinate is accepting, the first one I don't care. And their union is exactly what I want. Okay? Alright? Okay. Okay, so now let me quickly sketch how do we prove this, why are we doing all this? In fact, for all strings U, and I should say this, for all Q belongs to, so for all, in fact, I should say this belongs to Q. Technically, I need this. Okay, this I'll fix this. Okay. So okay, let me write this down a little bit later. Right, for all Q1, Q2 belongs to Q. For all W belongs to sigma star, delta star of Q1, Q2, W is so what is this saying, right? What is this statement saying? It is saying that the new machine is simulating the two machines. That's all it is saying, right? So how do we formally state it? It's saying that for every state in my new machine, okay, yeah, for every string in sigma star, not language, every string in the every string, what does my machine do? If I start the machine on Q1, Q2 and give it a string W, what does it do? It goes to a state where it is going to go to the state where the first machine would go on W, comma, where the second machine will go on W. Okay, that's what this is saying, right? This is simply saying the new machine is simulating both machines in parallel. Right? This is obviously our intuition for construction, right? But this is formally stating that mathematically, right? Remember what is the definition of delta star? Delta star for a DFA is a function which says given a state and a string, what is the output of that, right? What is the state that the machine will go to, right? This is simply rephrasing the fact that the new machine is simulating the two old machines. Okay, and you can easily prove it by induction. Okay, from the construction. Okay, now once you have this by construction, why is this enough to prove that this new machine will accept the right language? So if you prove this, then I claim that we have what we want. That this machine will accept exactly the strings in L1 intersection L2. So why does it, if you have this, why is that easy to prove? So let's see this, right? Will this machine accept every string that is in L1 intersection L2? Well, it will, right? Why? Because, let's see what the machine does on W. If it is a W belongs to L1 intersection L2, what does this machine do? If it starts on start state from this lemma, if it starts in the start state of the new machine S1, S2, where is it going to go? So it will go to, the machine starts in, remember what is the start state of the new machine? S1, S2, right? On W, what is this from this lemma? It is delta 1 star S1W, okay, delta 2 star S2W. Okay, now once we have this, when will this new machine accept? This new machine, by our definition of the accepting states, it will accept if and only if this guy is in A1 and this guy is in A2, right? But that's precisely, that means that, you know, the old machine was accepted it and the first machine accepted it and the second machine accepted it. Okay? Right? Yeah? Yeah, but the definition of acceptance is that if you land up in an accepting state, that's accepting, right? So, you know, when will this land up in our new accepting states? Our definition of a new accepting states is both coordinates should be in the first coordinate should be in the first accepting state, second coordinate should be in the second coordinate accepting state. Okay? So it's just symbol pushing, okay? It's not deep or anything, right? Once we know that this is what we're simulating them, this is all just mathematically formalizing what is what we want. Yeah, is somebody have a question? Yeah.
Output of delta star is
A state. Remember, delta star has two inputs, a state and a string, and it gives you what? A state. What is the meaning of it? It says, you know, if I start this machine on this state and give this input string, where is it going to take me? Because it's a deterministic machine, there's a unique state it will take me to, right? Yeah? Okay? All right. I won't do the inductive proof because it takes too long and you can look at it in the notes, okay? Okay, so just to make sure we understand, I want to now create a machine which accepts the strings which are in the first language but not in the second language, the set difference. Okay, okay. So think of a following example, right? I have so L1 is a set of all strings which end in 0, 1. L2 is a set of all strings which have odd length. Okay, so what is the difference of the first language minus the second language, right? What does that mean? I want to accept all strings that end in 0, 1, but don't have odd length. Okay, okay, you can say, okay, but it's the same as saying that they have even length, right? Which is a complement of the language, right? So how can we easily do this without doing anything? So from what we have seen so far, what is L1 minus L2? How can we rewrite it as? Okay, L1 minus L2 is what? L1 intersection what? Of L2 bar, right? Okay, but we already knew how to do intersection and we already knew how to do complement, right? So we can do this too, right? You can create a machine for this, yeah? Okay, but suppose I said, no. I want a formal definition just like that. Okay, I wanted you to do the following. What should the accepting states be? If you want to simulate both of them, at the end, what are the accepting states for L1 minus L2? Okay, we're simulating both, right? You know, I claim that by just figuring out what the accepting states are, we can do that also directly. Yeah, yeah, A2 naught is a Q2 minus A2, right? So the accepting states of the new machine are A1 product Q2 minus A2, right? Okay, so A2 naught, that is A2 naught. See, so when do we write A2 naught and why should we write Q2 minus A2? When you have multiple sets floating around, it is not always obvious what complement means, right? So that's why we have a little bit careful, okay? So we just write, you know, it is A1 product with Q2 minus A2, yeah? So just that's its way, okay? It's easy enough, yeah? Okay, we understand how to do this product construction. It's just simulation, right? Okay. Why only 2 machines? We can simulate 3 machines too, no? Okay, that will be in the homework so that you kind of make it concrete to yourself, right? It's not, there's nothing particular about 2. You can do it 3 or 4 or 10 if you want, right? Okay. That's about DFAs. So you can see that, the DFA way of thinking allowed us to do some things easily, right? Complement, union, intersection and stuff, which regular expressions didn't do. So now we'll do something even more powerful, and that's called non-deterministic finite state automata. Okay. So that's what we're going to do now. Okay. So look at this machine. What does it look like? Looks funny. Okay. Why is it looking different from a DFA? Yeah? Yeah. Yeah, so it seems to have funny things, right? On a 0, it's going to 2 states from Q0, right? That's one feature, right? From Q epsilon on 0, I can go to Q0 or I can stay where I am, right? Okay, and then there's an epsilon there, right? What does it mean to go on an epsilon, right? It's not part of the alphabet, right? It's an empty string. What does it mean, right? And the other thing is that on some states, on some letters, there is no transition. What happens if I come to a state and there is no one transition to go from on a letter 1? What should I do, right? Okay. So what is this machine, or does it have any meaning, and why should we think about this, right? That's the question, right? Okay. So the main differences you will notice are that epsilon transitions, on some letters no transitions from some states, and multiple choices from on the same letter from a certain state, right? So the thing is, is this a real machine? Yeah?
Yeah, I have a question. So I guess I will think that he might.
We'll describe. I mean, I haven't explained what this machine is doing, right? So it's a visual to say, this looks a bit bizarre. And why are we discussing? And what is the meaning of the epsilon transitions? What is the meaning of having multiple transitions from, everything looks a little strange. Is it a real machine is the question, right? If I gave you this machine, it is not clear what the machine, is it a machine in the sense that, when you think of a machine, you give it an input, it should mechanically go, one step, and we should know what it does, right? It shouldn't suddenly say, I feel like, going this way today, right? And that's not what we think of as a machine, right? So that's why it's called non-deterministic, because the behavior of the machine is not obvious based on the input. Right? It's not a real machine, right? So in the sense of what we think of as a machine. So, but first we have to understand, what does it do? What does it mean, right? And why should we think about it, right? So let's understand this in the following sense, right? So the meaning of the machine is that if I give an input string W, it can do many things. So what does it mean that it can do many things? It can go to many possible states on seeing some input. Okay, right? Okay, so that's what we need to understand. Okay, so let's do it slowly. So if I'm the start state Q epsilon and I see a 1, where should I go? What are the possibilities for the machine? There is only one possibility on seeing 1, right? Okay, and that is to stay around. Okay, so we say, okay, this should be only 1. Okay, sorry, it should be Q epsilon, right? Okay, that's okay. So far, so good. But what about 0? Where can the machine go? I give it freedom to either stay where it is or go to Q0, right? Okay. Okay, but then, so on Q, okay, but once it reaches Q0, what does the epsilon mean? Okay, epsilon means that it can jump if it wants to. Okay? Remember, if you are in a state and I say, what does it do on an epsilon, what did we decide? We just stay there, right? On a state, on an epsilon, we're not moving anywhere, right? It's just mathematics. There is no real machine here. Okay, so that's just the definition we're going to put on this machine. Okay, so I'm trying to say that, okay, look, I'm trying to describe what the meaning of this machine is, that we construct the meaning. It is not clear what it means, right? So I'm developing the intuition for the meaning. Okay, so the intuition for this is that on 0, I could be in many possible states at the end of seeing 0. So because I can be in many possible states, my output is not a state, but a set of states. Okay? So I want to know what are the possibilities. I claim the possibilities are Q epsilon, Q0, and even Q00. Okay? Because I can see 0 and then I say, I'll go on epsilon to Q00. Because I'm allowing you to. Okay? Sorry? What do you mean? There's an epsilon transition, right? From Q0, I can just walk over to Q00 because it's either or. Yeah, but I can stay on the 0 on Q epsilon, right? I can either stay in 0 or I can move to Q0 and then walk around and go to Q00 because it's epsilon. Epsilon means, I don't, this is an empty string. I can, I think of this 0. What is this 0? This is a string, not an alphabet. Okay, it's a string. Okay, it's a bizarre thing, right? It's not, it's just a strange machine, right? What does it mean? The epsilon transition means that I can take it if I want to. Okay? Yeah. Yeah, you can take, I'll show you more examples, okay? Yeah, we'll see, okay. Okay, so what does Q0 and epsilon do, right? What should it be? I can stay at Q0, that's the usual definition, right? But now what can I do? I can go to Q00, okay? Okay, suppose I had another epsilon transition here, what would be this? I can go 2 epsilons if I want, right? Because 2 epsilons is the same as an epsilon, okay? Yeah? Okay, yeah? You can stay where it is. Yeah. Okay, the previous one maybe makes more sense now, right? Does the previous one make more sense now? Well, okay, remember this is a string 0, not alphabet 0, it is string 0. Okay, so what's the string 0? I can put epsilons at the end of it, no? Yeah. No, it's not okay. I'm just saying that these are potential moves it can make, and so it could be any one of those things. Well, no, that is not as 00, that's the name of the state. On 0? Okay, it first goes to Q0. Yeah, but it's a string, right? And I can move on epsilon if I want to. There's not, 0 is the same as 0 epsilon, no? The string 0 is the same as string 0 epsilon. Yeah, they're both strings. No, it's not an alphabet, it's a string. Okay, so he said, right, machine on input string W. Okay, let's see one more example, then we'll see. Okay, what about the string 01? Okay, what should the machine do on string 01, or not? What does the machine do? Where can the machine go to on string 01? Okay, now it's a bit messy, but let's figure it out. Okay, there are lots of places it can be, right? Okay, Okay, it's hard to figure it out, but let's see. 0. Okay, how do we figure it out? Okay. Yeah, but let's not do it like that because then we will get confused. Okay. Let's say, where can it be after it sees a 0? So we already figured that out, right? What was that? Okay. It can be any of these 3 states on 0, right? Yeah? Okay, so let's think like that. Okay, after 0, it can be in any of Q epsilon, Q0, Q double 0, right? Now think of what happens if you see a 1. Well, it could have any, let's figure out for every Q state in this set, what can we do on 1, right? So if I was in Q epsilon and I see a 1, what happens to me? I stay where I am, right? That's it, there's no other choice, right? So I can say, okay, one possibility, let's figure this out. One possibility is that I am in Q epsilon because I could have been in Q epsilon after seeing 0. And now I see a 1 and there's no choice, so I'll stay in Q epsilon, right? Okay. But what if I was in Q0 after seeing a 0? And I see a 1. I can't go anywhere, right? Well, you may worry that I could go to Q00, which is fine. It's already there. We'll figure it out. Okay. Okay. I could go to Q00 and then go to QP, right? Okay. So I say, maybe I can go to QP. If you're worried, you can say QP, right? Okay. What about Q00? If I see a 1, where can I go? QP, right? So I get QP again. So that's it. So we can do it systematically, right? We figure out, okay, after seeing so far, we could be in this set of states, and then we have to say, okay, we're going to see the next letter, but there are epsilons involved, which makes life a little bit complicated. But what else can I do? Okay, I can follow epsilon things, and I can get another set of states, right? So these are the possible set of states after I see 0, 1. Okay, yeah. Mm-hmm. Yeah, yeah. So we have to figure out what it means. Yeah. Q0 a part of the. So can we be in Q0? How can we be in Q0 after seeing 0, 1? No, because there is no transition on 1 to stay there, right? If there is no transition from a letter, it means that I die on that letter. Okay, that's the meaning. Sorry, that's a good point. Okay, if I see no transition, what does it mean? Okay, there's no way to go anywhere. Okay, yeah. Okay, no, okay. So now, so this is the thing. We're developing the meaning of what this does, right? So you think of this as at each choice the machine forks into 2, right? And then it can do whatever. At each potential thing, if you had 2 choices, I'll go this way or that way. And if I have an epsilon, I can take it or not take it, right? So, and all of them will go somewhere, and any of the possible reachable states is in my set. That's the meaning of what I can get to after I see the. Okay, graph theoretically, what does it mean, right? Mathematically, what we're saying is that start at a state and you follow, a state is reachable if you can follow a path to the state where whenever you pass an edge, you get a string, right? You add up all those letters. If that equals the input string, then you can get to the state. Okay, we'll formalize it a little bit more formal. Yeah. It's implicit. If there is no way to go from so that we don't have to write it down all the time. Okay. If from a state on a 1 there is nothing to do, you say there is no way to get out of the state on a 1. That means you die. Okay. So in particular, for example, let me write this down. What is this? Good question. What is Q00 on a 0? What should we say? Okay, what is the set of possible states I can reach? empty set, right? Because nothing can be, okay, so that, okay. So the difference between a DFA and an NFA is on a state and a string, we can go to multiple states, not one state, right? Okay, so I hope we got the intuition of what it means to go to a state with, yeah, 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 yes, it will, yeah. If you had the 0 and 1 there, no, it'll be empty set still. It's a good question. So, no, because there is no, I mean, on the very first letter, what is it going to do? It's going to die. And that's it. Okay. Okay? Yeah? Okay. So, it's kind of bizarre, no? What is this? Okay. It is called non-determinism. Okay? And it has many powerful uses, and we'll see that very soon. Okay. When does a string accept? The same thing. Okay. How do we know whether this machine accepts a string? If there is some way to go from the start state on the string to some accepting state, just like a DFA, right? The only thing is, because now we could be in many possible states, if there's any way to get to an accepting state, we say yes, the machine is accepting that string. Okay? Is that all right? Okay. Okay. So now the language, what is the language accepted to the machine? The same thing. If you can make all the strings that on start state can go to an accepting state, they are the language. Right? It's the same thing. It's just that it's bizarre. I mean, it's a little bit bizarre. Okay, is 0, 1 accepted by this machine? Why? Yeah. Yeah. Yes. Right? So think of this as a walk in the graph, right? So this is a potential walk in the graph, and let's write down the walk. 0, epsilon, 1, right? And what is the string? This is just 0, 1, and it went to accepting state. Yeah? Alright? Okay, what about 0, 0, 1? Yeah? 0, 0, 1, and this is 0, 0, 1, and I get to an accepting state, right? Okay. What about 1, 0, 0? Is there any way you can create a walk? 1, 0, 0, what can you reach? You can only reach you could reach more states, no? I mean, what are all the states you can reach? Q epsilon, Q0, Q0, 0, right? You can reach those 3 states on 1, 0, 0, but none of them contain the accepting state. So we don't accept this. Okay? Okay. So what is the language you think this is the machine accepts? Do you have some intuition for it? Yeah? Yeah. On 1, 0, 0 it will die. Yeah, it will die. Yeah, anything starts with 1 will die, yes. Okay. Yeah, what is the language accepted by this machine, you think? So I claim, or can anyone has a guess for this? Yeah? No, so I mean, are all of them accepted? Is I'm asking. Yeah. Okay, but is it all, or are there more accepted? Yeah. Any string containing uh, 0, 1 or 1. Well, why should 1 be accepted? 1 is not accepted, no? Okay, let me write it down and let me see. Okay. Does it make sense? Sorry? Plus 1 or? Okay, how can we get from Q epsilon to QP? What is the only way to get from Q epsilon to QP? You have to have either 0, 0, 1 or 0, 1. Okay? And you can have any number of things in the middle, in the beginning, and any number at the end. Okay? Is it okay? So, yeah? Okay. Okay, so it's a bit hard, but we'll not typically try to understand what NFAs do, because it's very hard to do that if somebody designs an NFA, which is the bizarre thing. Okay. But the meaning, okay. Okay, so here is one thing that is a little tricky with NFAs, right? With a DFA, if I give you a string and say, what does the machine do? You can say, okay, let's go, da, 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 da. It goes somewhere, and you tell, it's accepting, not accepting, it's clear, right? With NFA, suppose I say, is this string accepted by the NFA? Now, what I can do to you is like, look, this is the reason the string is accepted, because let me show you a path. In the machine, look, on this string, I am showing you one way to get from the accepting state, start state to the accepting state. There could be many, but to convince you, I can just show you one way of getting to the accepting state. But how can I convince you that a string is not accepted? Yeah, but to convince you that the string is not accepted is more work for me, right? I have to tell you, there is no way. So what does it mean? I have to give you all possible ways of going around and say, so that's an asymmetry in the definition of non-determinism. Okay, that's why non-deterministic machines are, the one interpretation of non-deterministic machines is that they're making it easy to give you proofs of acceptance, but they're actually not making you easy to proofs of rejection. Okay, so how much that buys you is something that is very fundamental, and we'll see why it is useful. Okay, but let's now define mathematically what an NFA is. Okay, what is mathematically an NFA? It looks like a DFA, but there's one important difference. It's also a 5-tuple, states, okay, sigma, okay, alphabet. The transition function is a tricky one. Start state is fine, it's a state in the thing, and accepting states are fine, right? The only tricky part is, what does it mean that, what is the transition function? Okay, now what is the transition function? It's a function from sigma union epsilon to what? Okay, that means that, I'm going to tell you on a state Q, for every letter A and also epsilon, the potential places you can go to, not just one state, because it can be many states, right? So it's a set of states, not one state. So the function is from Q times sigma union epsilon to the power set of Q. Why? Because the output of this function is not one state, but a set of states. Okay? So, okay, let's see an example. That's the only difference, okay? The transition function is going to tell me on a Q, but also the other difference is that we are allowed to move on epsilon. Okay? So, it's a function from sigma union epsilon. Okay, here is the example again. What is the set of states here? That's easy. What is sigma? That's easy. What is delta? I will come to that. What is the start state? Q epsilon. What is the acceptance states? QP, right? This is all easy, right? Now, how do I tell you S? Like, I have to tell you what? A table, right? So, what is a table now? My table has the states here, and here it is sigma union epsilon. So, I have epsilon, 0, and 1, right? No, because that's the definition of the machine, because the machine has epsilon transitions, right? But I have to specify what the machine does on an epsilon, no? Or from a state. See, on a state, I can move on either letters of the alphabet or also on epsilon. So this is just the specification of the machine, the description of the machine. So you understand the graph, right? So the graph, I'm putting it in mathematical notation. The graph is telling you that from a state I can move on not only letters of the alphabet but also on epsilon. So I have to capture that in the description, right? So my function is from states times sigma union epsilon, because I'm also allowed to move on epsilon, which DFAs were not allowed to. So I have to tell you, can I move on epsilon, and where can you go on an epsilon? Okay. Okay. So from what do you think this is? On epsilon, where can it go? Sorry? Okay. Okay. It's a convention. The convention is that it is empty set. Yeah. Well, not convention. We don't have an arc with label epsilon out of the state, right? Okay. We don't have an arc with label epsilon on this, right? Okay. So, yeah. No, that is the meaning of the behavior on epsilon. But the specification says that there is no epsilon transition out of this state. Okay, that's the meaning of the specification. That is there an arc labeled epsilon from this state going somewhere which is not itself? Where all can it go? Okay. No, not only that you can that's one difference. The other difference is that on a letter you can go to multiple places. On a 0, I don't have one distinct thing. I can go to multiple places. And on a letter, I can just die. Okay, those are right. So, okay, what about on 0? Everything is set. What are the set of states I can go on a 0? Q 0. Okay, and what about on 1? Okay, okay, and what is the Q0? On epsilon, now it is an arc is there, right? Okay, so what do I put? Okay, and on 0? And on 1? Empty set. Okay, good. And everybody gets the idea? Yeah, okay. You then say, okay, Q00, Q, yeah. Sorry? Yeah. Yeah, so that is the difference between what the machine will do on a string versus how we describe this graph, okay? So we're just describing the arcs of this graph, right? But how it behaves on a string is a different thing, yeah, okay? All right? Yeah, it takes a while to get used to it, but it's not, it is a messy way of thinking about it initially, but, okay. Now we want to formalize what we have been discussing. What does it mean? I mean, what does this machine do from a state Q on a string, right? Right? Yeah. Sorry? Oh, you add epsilon to that the set sigma. Remember, sigma is a alphabet, no? So normally sigma, epsilon is not there in sigma ever, right? Because it's a special symbol, right? So when we say sigma union epsilon, we are saying, you are allowed to now move on epsilon also, right? Yeah? Okay. 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 So we want from this a mathematical formalism for, we know on the specification of the machine, what does the machine do on a string W, right? So we want notation for delta star Q W, right? So what is the meaning of that? On a state Q, if I give you a string, what is the set of all possible states that I can be in? How do we mathematically define it? We kind of saw it, right, intuitively, but how do we mathematically define it? Okay, it's a pain, okay? It is not completely easy. So let's first figure out something a little tricky. Okay, look at this machine, okay? Okay, so it has more epsilons, right, than the other one. So I delayed this so that we get a little bit. On start state, from start state S on epsilon, where can I go? I can stay in S, yeah. I can go to D. Where else can I go? I can go to A, yeah. So it's clear that on epsilon from start state S, those are all the states I can reach, right? Okay. If I give you a big graph as a graph theoretic problem, what is this? How do I figure that out? I give you this graph which has labels, right? Epsilons and other things, and I say I start this state on epsilon. Where can you reach? What is that? You know, it is a reachable. If I look at only the epsilon arcs and remove everything else, what are all the states that I can reach from this node, right? Yeah, that's precisely the set of all the states I can reach on epsilon. Yeah. So we'll call that the epsilon reach of that state. Okay, what is the epsilon reach of S here? S, A, and D. Graph theoretically, does it make sense? I can take any number of epsilons as long as I go along epsilon arcs. I can go anywhere I want, right? I can't take a letter thing. I can take epsilons any number of times because epsilon any number of times is epsilon, right? What is the maximum size I'll get? The set of all states. Yeah. Yeah. That's by definition. Remember in DFAs, if I don't give you any string, I'll stay where I am. That's just the definition of the machine. Except for this, it's just convention. Okay, I can put an epsilon arc on every state, right? Will that make you happier? Okay, but it just somebody decided at some point that's a waste of time. Okay, it's not any. It's just taste. Okay. If it's implicit, then we don't have to write it all the time. That's all. No, that's just a specification. Okay, it's a convention. Okay, so the meaning is look. It's like syntax, right? You know, maybe I don't like somebody's syntax. Well, it's a standard. So what am I going to do, right? So it's just a convention. There is no deep reason for it. Okay, so I could, for example, for everything I can put an epsilon on the state and then it will make you happier, right? It's more consistent for you. But, you know, history, right? Okay, somebody decided that that's a waste of time, so we'll just follow that convention. Okay, but the meaning is that, you know, if I have epsilon, I can stay where I am. It's just, okay. So it's just a definition, it's not, yeah. Yeah, exactly. On the string, yeah, right. Yeah. But I'm only calling. So the definition is only on epsilon reach. What is the epsilon reach of S? It is S, D, and A, right? What is the epsilon reach of E? Itself, right? What's the epsilon reach of F? Sorry? G also. Okay. Yeah, it's not hard. It's just, you know, where all can I go on epsilon? You just do a graph search, right? Okay. Yeah. I can mathematically define epsilon reach, but it's a headache. But it's okay. Everybody understands epsilon reach. Yeah. Okay. That's just the first step. Okay. What is the inductive definition of delta star now? Okay. You have to go slowly. Okay. If it is epsilon, the string is epsilon, what is it should be? What is our understanding? It should be the epsilon reach, right? From a state Q, what is it? All the places I can go to on epsilon, all the epsilon reach. Yeah, that makes sense. It's a set. Remember, it's a set. Okay, the hard part is understanding what we should do on a string which is of one letter, basically. This is already tricky. Where all can I go if I see a string which is one letter? I mean, string of length 1, not string of one letter. String of length 1, which is different from the letter, right? Okay, what is a string of length 1, right? A string of length 1 is, you can think of it as many epsilons, a letter, and many epsilons, right? Where can I go on such a string? So if I'm at state, I can go on epsilons, 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 epsilons. Yeah? As long as I'm allowed to go. And then what should I do after that? I jump on the letter, and then again I can go epsilons, 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 epsilons till I get somewhere, right? Yeah? All those places should be in my set, no? What is it? That is that, okay? All right. Okay, you have to just look at what that is. What is that? You look at all the states which are in the epsilon reach of the initial thing, okay? So that gives you a set of states, right? And then say for every one of those, look at where all I can go, because remember on a letter I can go to many guys. I look at all of them and then again take all their epsilon reach. Okay? It's a headache, okay? But that is mathematically the proper definition. Okay? So it's not hard. Okay, let's go back to an example, right? It is intuitive, but mathematically it's a bit painful. So what is this? Delta star S, let's see. This is not a good example. No. Okay. F and okay, let's see delta star of F1. What is this? Okay. Remember, 1 is a string, right? Of length 1. What is the thing? Well, first we go on F to what? Epsilons, right? Where all can I go? First I go on epsilon. So what is epsilon reach of F? F E C D G, right? And A too. God, okay. Okay. Now I've reached all I can with epsilons. Then what should I do? I should try 1, right? Okay. For each of them, I should see where I can get with 1. Okay. What happens on F on 1? I die. So that's good. Okay. We get it out of there. E on 1. Now I get back to F is a possibility, right? Okay. So we'll write, okay. And then what about C on 1? Empty set, right? On 1, you can simplify empty set. So you don't go anywhere. D on 1. D on 1 is E, right? And then so on and so forth. Then we get a bag of sets again, right? Bag of states, right? And then we take epsilon closure of all of them, right? Because from there we can go on epsilon 2, right? That is the definition for one string of length 1. Okay? But then it is easy, right? Once you know what you do of string of length 1, then you do the next guy, right? You follow it. That's it. It is painful, but we need to understand. Okay? Yeah? Okay. We're not done yet. Give me 1 second. I didn't even go through half the lecture. Okay. Okay. Let me formally define. Okay. What is the language accepted by the machine formally? On start state, on the string, if I get to an accepting state, that string is accepted by this NFA. Yeah, now we know what it means to go, what is the set of states that I can go from my state on a string. Then I can define formally that anything that takes me from the start state to an accepting state is accepted by the language. Okay, that is done. Okay. All right.
What you're saying about how on the graph, people just